go ahead. I mean, I can't say the title again. I just not.
No, I will not say the title again. This is here. You can see it, right?
You go.
So yeah, this is a paper that I started a long time ago, and as you may know, the discrepancy of carbon budget in the mesopelagic zone is not an easy topic, and so I had a lot of discussion and stuff. So I'm really happy it came out. And when I tweeted this paper, Svenja automatically asked me to present it. So thank you for the opportunity. So as you know, in the mesopelagic zone, there is no light and therefore no photosynthesis. So the export of thinning particles is considered as the main source of labile carbon in the mesopelagic zone. And among other, it will be used by the attached prokaryotes, which are solubilizing the POC, and indirectly by the free-living prokaryotes who are using it, at least the part solubilized, which is not used by the attached prokaryote. So the quantity of carbon exported by the sinking particles I'm representing here is decreasing with depth as it is used, fragmented, transformed by organisms until only the refractory fraction remains and is sequestrated at depth. So the comparison between the carbon exported in the mesopelagic zone and the carbon demand of the organisms should tell us what is not used and therefore what continues to sink. However, all the processes that I've described are difficult to quantify today. And one phenomenon that illustrates these difficulties is the discrepancy between the carbon demand, which is in pink here, and the export of particles. By focusing only on prokaryotes, studies systematically show a difference between the two of a factor 2 to 4, which is impossible. You can't have more carbon used than carbon available, right? So if we zoom a bit on this pink bar, it corresponds to the carbon demand of heterotrophic organisms. They use carbon for biomass production, growing, reproducing, and for their respiration. To estimate the carbon demand, we add their heterotrophic production to their respiration. And here I'll focus mainly on prokaryotes, but you could add the other organisms here. So for their production of biomass, it's often measured by radioactive leucine incorporation rates, and this rate is measured assuming stable protein biomass and leucine protein ratios. And then the result is multiplied by a conversion factor leucine to carbon to obtain the PHP, so the prokaryotic heterotrophic production. And for their respiration, it's not often measured, and there is no real consensus yet on how to measure it properly. So it's estimated from the bacterial production here and a prokaryotic growth efficiency. And without much data on conversion factor, and PGE, and even less in the mesopelagic zone, we often take median or theoretical values that don't necessarily match the zone of the study, the depth or season, and we often, if it's not always, neglect the influence that these parameters can have on the extent of the discrepancy we have here. The main question of this paper was, what are the influences of the different parameters involved in the calculation of carbon budget, and how can we improve that? So I used data from a cruise in PAPSite 2015. So for the carbon input in green here, which is in fact the sum of POC export and DOC export, I took the gravitational POC export calculated and measured by Becher et al. 2016 in the marine snowcatcher, and DOC estimated from a previous cruise in 2009. And I wanted to add, because we have this paper from Boyd et al. 2019 about PIPs, particle injection pumps. And so I tried to see how much it would be to add that. So I calculated around 52% of the gravitational POC. So I added these sources as well. And regarding the carbon demand, thanks to the use of marine snowcatcher data, I was able to separate the prokaryotic carbon demand of the free-living prokaryotes from the prokaryote attached. So for those who are not really familiar with this instrument, it's a 100-liter bottle, which you use it to sample at a depth you want, and then you wait 2 hours on the deck of the boat, and you have the separation of the particles, so sinking fraction here and non-sinking fraction here. And so for the free living, I had the incorporation of leucine that I used, and for the respiration, I will have to use this formula because I don't have any measure. However, for the attached prokaryote, I have as well the incorporation of leucine, and I was in this study they measured particle by particle sum respiration. So I have to point this out that it's only the second study which managed to have both, and so we will be able to calculate prokaryotic growth efficiency for this fraction for the second time. I will not focus on that, but I tried to estimate what would be the respiration of zooplankton, so I will add that to the pink bar in the budget you will see. So with this data, I can calculate a carbon budget integrating attached prokaryote for the very first time. However, this carbon budget will depend on the choices of conversion factor for both free living and attached, and PGE for the free livings. So I first used the theoretical values of conversion factor and median of PGE from the literature, as is conversely done. So we have the conversion factor of 1.55, which is the theoretical values. PGE sinking from of the particle attached from the literature, and the median as well for the non-sinking, so the free livings. And you see that you have a big discrepancy as usually. So the carbon input seems to support the carbon demand of attached prokaryotes and zooplankton, but not of free living due to their huge respiration. Yeah, this is what I said. And then I tried the values used by Gehring et al. In 2014. This is the only study that have reconciled the carbon budget. This is completely different, but it uses a measured conversion factor different from the usual theoretical one, which is here 0.44, which is a mean from few values of the mesopelagic zone, and then a really high prokaryotic growth efficiency for the attached prokaryote, which is unfortunately coming from river measured, but I guess at this time that was the only data available for particles. So as you can see, the choices of parameters can lead to really drastically different carbon budget, because at first it's the same data, it's just the parameter you use which are different. But without this data, it's challenging to choose the adapted value. So how can we do? In parallel, there is another approach to estimate carbon budget. It's the modelization. However, since we know very little about how the biological carbon pump works, in the mesopelagic zone, models are difficult to constrain. For instance, for the biological carbon pump in the mesopelagic zone specifically, they are not too many, and here I choose the Anderson and Tang 2010 model because it assessed the part of remineralization of different compartments, such as zooplankton, prokaryote attached, or prokaryote free living. However, again, it requires as well 24 parameters such as the PGE. So it's again complicated to use that for accurate estimate. So whether with measurements or with the model, we depend too much on the choices of parameters on which we have too many uncertainties. On the other hand, some of the fluxes estimated by the model correspond to data that I have for the PAP Cruise 2015. Such as the bacterial production for attached prokaryote and their respiration, same for free living, and total respiration of zooplankton. So since we've got correspondences, we can take the problem in reverse. So we have a few measurements for which we are confident, or let's say we are confident, and these same measurements are model outputs. So we are going to force the model to optimize the combination of parameters that allows the model outputs to have the closest possible value to our measurement. Don't know if that's clear. And we can then see if the proposed parameter values make sense, and if so, we can use them to build a carbon budget. Of course, this is not so easy. We only have 4 measured fluxes, where the model has 80 outputs, which is not enough to constrain the entire model and estimate the 24 parameters. So to choose which parameters to work on, we performed a Sobol sensitivity analysis. Without going in too much detail, the higher the index is, the more sensitive the parameter is, and the more the impact it will have on the carbon budget. And in our case, 4 parameters stand out. So we have, for instance, we have C, which is the proportion of particulate carbon export, which is used by prokaryote attached. Both prokaryotic growth efficiency, they are here again, of course, and alpha, which is the proportion of carbon hydrolyzed by prokaryote attached, released to the surrounding water. They are not using everything. So the idea is to fix the 20 other parameter to estimate only those which are the most sensitive, so those 4 ones. So we proceed to the model inversion and we obtain a Psi value of 0.67. Okay, so there's only one value in the literature to compare, and it's 0.76. So we're in the same order of magnitude. We can say we're okay. Oops. Then for the alpha, we obtain 0.77, which is between the values estimated for surface particle or pure cultures, so really fresh and organic matter, and the values of 0.41 that I managed to calculate from Mediterranean Sea cruise, which is a particle poor zone. So therefore, it seems possible for the mesopelagic area during a period of high particle production to have 0.77. PGU thinking, there is, as I said, only one other study who measured them, and they found between 1% to 3%. So with our 2.6%, we are not too bad. And for the non-sinking, in the ocean, the ranges are from 0.1% to 64%, which is huge and coming from various environments and methods. And if we focus only on the mesopelagic North Atlantic, the median is 7%, so we are not too far. And if you see here, this is the error between the outputs and the measurement that the model optimization did. And this is really low, so we are pretty happy with the optimization method we did. So now we have that, we can try to calculate a new carbon budget with those values. So here is the new one, and you can compare with the 2 others that I presented before. There is no more discrepancy here, as you can see an excess of POC fluxes not consumed. And so this corresponds to a much more plausible carbon budget than the first one, for which carbon is missing, or the second, which uses parameters from rivers or that don't match perfectly the in-situ condition. However, a multitude of uncertainties remain for each of the components of the carbon budget. I only presented prokaryotes, but you can imagine a lot of uncertainties around the other groups. And if we focus only on prokaryotes again, you can see on this figure, the quality is really bad. But anyway, the quantities enclosed in green are well known. So you can see that there is only one. Those in blue lack data, and those in pink are completely unknown. So the understanding here is currently better for the free-living prokaryotes, whereas data are still insufficient for sinking prokaryotes, and even absent for prokaryotes attached to neutrally buoyant particles, which should have another role into that. And moreover, to build carbon budgets, these variables are integrated over a few hundreds of meters of water column, and the relationship between those quantities and the pressure, the increasing pressure or the depths are poorly known and neglected right now. So this is something to dig as well. And last things, I can say in parallel, we don't know much about virus role and chemolithotroph who could add another carbon sources into the budget. So as you can see here, there is a lot of uncertainties and stuff to explore there. And so that's why we are here, I guess. And to conclude from the paper, we demonstrate that the most sensitive parameters in the model are the ones related to prokaryotes, such as PGE, so prokaryotes are important. Inverting Anderson and Tang's model lead to consistent values of the parameters, and using these values instead of the classical mean from literature or inadequate theoretical value result in a more consistent and realistic carbon budget than previously considered. And in terms of personal messages, I would say we need more interaction between field observation and models that I try to do, but we are still missing some. I guess we could explore more. And more effort is needed to better understand the variation in little parameters or little conversion factor we are using everywhere, but whose influence can be huge. So thank you.
Awesome. Thank you so much. Oh, I have an echo here. No, that was great. I really enjoyed it. If anybody has any questions, either raise your hand or turn on your camera or write it in the chat if you can find the chat somewhere. Yeah, it must be here somewhere. Yeah. Oh, yeah. I see it actually next to the people. Okay. Yeah. No, that's pretty good. Are you focused on prokaryotes and sinking particles mostly, obviously, but then what about all the, you said you also calculated the particle injection pumps. What about active flux and how much did you consider all the critters migrating?
Yeah, so I had unfortunately no measure of that directly for the paper, but I wanted to take them into account. So I took values that I tried to adapt with little percentage to the POC fluxes from the previous course in 2009. And I tried to include them like that, but we did this last summer with the Apéro French project. We had 2 boats and we tried to have all those little fluxes to have a more complete stuff at the same moment to avoid to take from other place and other study.
Yeah, yeah, it is. I mean, it is hard. There's a lot of double accounting going on, I guess, as well, because yes, you know, when they stop migrating and they're standing like hanging out at a certain depth, I mean, they're still producing the passive flux. So it's just, yeah, it's a bit hard to tease it apart sometimes. But yeah, interesting.
Yeah, in the model, it's just maybe it should be a bit improved in the model because the active fluxes is only something that you add at the start. Like you say there is as much carbon entering the mesopelagic zone and that's it, that's fixed. So maybe it should be a bit more dynamic or something. Yeah.
Yeah, okay. Yeah, fair enough. Does anybody else have any questions? Now's your time. People are really shy. I'd see.
That's because of my fish.
Obviously. Very Christmassy. All right. I mean, otherwise, we probably move on to the next talk. And if people still remember a question, then they can just put it in the chat or write you an email, I think. So yeah, that should be okay. Awesome. Thank you so much. That was great.